Now let's go for input of boundary conditions in our setup. For that we have chosen our solver as CFX. So left click on the CFX and drag and drop it. Here we can find the setup. In order to connect our mesh file to the setup, go to the mesh, left click and just drag it to the setup. This way you will see a line here, and now the mesh is connected with the setup. And you see this sign here in the mesh. So you will have to update the mesh by right clicking and go to update. In that way the mesh file can be seen in the setup. Now double click the setup. Okay, here we have our file. Now we need to set up different parameters. So go to tools and go for quick setup mode. It is just the simulation of simple pipe flow. So we went for a quick setup mode. But if it was for any turbo machine, then we should have gone to turbo mode. So now let's set some parameters here. In the problem type, let's go for single phase, as the substance running inside this pipe will be water, which is a single phase component. In fluid, let's go for water, and we have this mesh file automatically here. Let's go for next. And in the type we will go for steady state, which means that the properties will not be dependent on time. Steady state means the properties are time independent, while transient means time dependent. We will just be seeing the simple flow, will not require any time frame. So let's go for steady state. And in the reference pressure, we set it to be 1 atmospheric pressure. It is just the baseline pressure. So let's set it to be atmospheric pressure. Later, the outlet pressure which we will obtain will be the gauge pressure, and if we add the gauge pressure with the reference pressure, then that will be our absolute pressure or total pressure. We will not be using any energy phenomena, so let's go for none in the heat transfer section. And in the turbulence model, we will be using shear stress transport. We also have other turbulence models like K epsilon model and K omega model. The K omega model is suitable in near wall regions inside the boundary layer. And likewise, the K epsilon model is suitable for the regions far from the wall. While this shear stress transport model can be taken as the average of both models, the K omega and K epsilon model, this model of turbulence will have properties from both of the models. But this shear stress transport model is not very accurate like K omega or K epsilon model. It is just that shear stress transport model is proven good in any region of the fluid flow, unlike K epsilon or K omega models. So we will be going with the shear stress transport model for this small project. So go for next. Then we will have to set boundaries here. So let's just so inlet, outlet, as well as wall, which we have already created in mesh. We just need to show them here in the boundaries. So right click in the boundaries, add boundary, and give the name inlet, and OK. You can see here it has already recognized the inlet, as we have already given this name selection in our mesh. And here we can give our input like normal speed, mass flow rate, or total pressure. Let's go for mass flow rate, and let's give 100 kgs per second for now. We will see how we will get the flow in our results. In the flow direction, let's go for normal to boundary. Means the flow will be perpendicular to this inlet surface. Now let's simultaneously add outlet as well as wall. Outlet. Okay. Likewise, it has already recognized outlet itself. And at the outlet, let's give average static pressure to 0 atm. It is the relative pressure, as we have already given the reference pressure as 1 atm, which is atmospheric pressure. Now at the outlet, relative pressure of 0 atm means we will have the absolute pressure of 1 atmospheric pressure at the outlet. And the last boundary will be wall. Okay, and it has recognized the boundary itself. So now we will have to delete this default domain default, as we have manually inserted all our boundaries. Now we have our boundaries ready. So let's go to next and let's finish. Here we can see the directions of inlet here and outlet here. Now let's go for solver control, where we can give the number of maximum iterations. Let's give 500 iterations, and let's keep the residual value to be in the order of 10 to the power minus 5. Now the iterations will carry on in the solver until the residual target will reach this value shown here. And in case it does not reach this residual target, we will have maximum iterations of 500. So let's apply it and okay. We can also see the solution units where mass will be in kg, length in meter, time in second, temperature in Kelvin, but we have not considered any energy input, so I don't think this temperature will be useful here. And go for OK. And now we will be going for solution, which will be solving our boundary conditions that we have given as input. So we will be seeing the solver interface in our next video.